Bismillahirrahmanirrahim. Dear viewers, today we will see RCC building design in Etabs v19. This will include design of slab, beam, column, single and combined footing and stair. What we will see in this tutorial: complete modeling of a residential building in Etabs v19, slab design from Etabs analysis result and detailing, beam design from Etabs design result and detailing, column design from Etabs design result and detailing, isolated and combined footing modeling in Etabs design from Etabs result and detailing, stair design independently using Excel sheet. Both ACI code and IS code will be applied for all of these designs. What are the paid resources we can get on this tutorial? Excel sheets, Etabs model and AutoCAD file. What are useful features of the Excel sheets? Full checklist for modeling RCC buildings in Etabs as per ACI and IS code. Easy slab design using Etabs result that will clearly help to make detailing. Easy beam design using Etabs result as per ACI and IS code that will clearly help to make detailing. Easy column main bar and tie bar design using Etabs result as per ACI and IS code that will help to make detailing. Easy isolated footing design using Etabs result as per ACI and IS code that will clearly help to make detailing. Easy combined footing design using Etabs result as per ACI and IS code that will clearly help to make detailing also. And easy stair design as per ACI code that will clearly help to make detailing. Stair design as per IS code available in a separate Excel sheet which is free. Links will be added in the description below the tutorial. So let's start. This is the plan of the building which we will model in Etabs v19. So let's open the program, new model, display unit. We can go for metric SI, concrete design code. First we can go with IS code. After finishing IS code, we can save the model for designing in ACI code. So let's start. Here we can see the grid number 1 2 3 4 5 6 along x direction, 6 grid line along y direction. This one I will keep in another display I am using so that I can model this structure faster. Along y direction we have 5 grids, 5. We can custom grid spacing. Here display grid data as spacing, 3.25 meter, 3.75 meter, 4.4 meter, 4.4, 4.7. Similarly, along y direction we will provide the input grid spacing, 2 meter, 2.8 meter, 4.8 meter, then 5 meter. Now click on OK. Number of stories. This is 4-storied building, including grade beam. It will be 5 stories, including stairhead. It will be number 6. Write 6. Typical story height, first 2 story 3.4 meter, and this one we will provide the foundation depth 1.8 meter. Click on OK. this model we can save. Now we can edit our story name. Right click, modify grid, here plain beam or grade beam, first floor, second floor, third floor, fourth floor, and last one stair top. First two floor height 3.4 meter, then 3.2 meter, 3.2 meter, and last one 2.6 meter. Click on OK. OK. Now we can start our model from plain beam. Here we will get checklist as per ACI code and as per IS code. First we will go to material properties. Go to define material properties, add new material. We can select India, material type concrete. Here the grade we can use M25 grade concrete. Material strength here 25 MPa and modulus of elasticity 25,000. Here you can see 25,000. If we use for example 28 MPa, accordingly the modulus elasticity will be changed, and that one we have to provide here, and from here we have to change the strength 28. Okay. Now for rebar strength, add new. For this rebar the grade 415 MPa. Click on OK. Now we will define frame section. Go to Etabs, define frame section. We can delete all the default frame section to find out our customized section in the list easily. Delete multiple sections. Select this, delete, and from here delete. Okay. Only one section will be available here, this one. After adding new section we can delete this one also. Add new property. For beam we can provide section size 20 by 50 centimeter, M25 grade concrete, depth 500, width 200 millimeter. Modify rebar, this one beam and clear cover. We can see if we use 16 millimeter dia bar for beam main bar, 38 millimeter clear cover. Cover to longitudinal rebar groove of centroid. Round up 40 mm. Click on OK. OK. Now this one we can delete. Add copy. Another beam we can add. Add new. For column C 25 centimeter by 40 centimeter. For column we can check here as per IS code. For column 40 millimeter clear cover. Here it is written clear cover for confinement bar, that means tie bars. So from tie bar to edge of the column it will be 40 millimeter. And reinforcement to be designed, and other things we do not need to change. Click on OK. OK. Another one we can copy this name and add copy of property, paste here 25 by 50. Rebar here we have to change to 415 MPa. Okay. For previous one also Click on OK. Now we can define slab section. Modify. Here we can design our slab thickness as per IS code. Here the maximum area of slab is here 4.7 meter by 5 meter. So this one 4.48, that means 4.5, and this side 4.83. Now for determination of slab thickness we need shorter span. Shorter span is 4.5 meter. Span to effective depth ratio we have to choose from here. For 2A slab of shorter span up to 3.5 meter. So as this is more than 3.5 meter, so we have to come here. Span to effective depth ratios for span up to 10 meter. For continuous slabs 26 173 millimeter. We will round it up to 175 millimeter. Yes, 175. And concrete strength M25. Click on OK. Column 25 by 40. For interior columns we will choose 25 by 50 column size. After design, if it requires to increase, we will increase, or if we can decrease, we will decrease the section size. Support, we will provide fixed support. Now we will draw beam 25 by 50. Now we will draw using this one node to node from here to here, and we have cantilever beam also. The beam layout, this one, this portion is cantilever, so this one we can right click, edit option to get this shortcut, replicate 2 meter. In this case we will use larger section for cantilever part. This one, this one, this one we will make same section to continue over the cantilever. Assign frame, this one 20 by 60. This one we can make 20 by 50. We can change our column orientation. Using this assign frame local axis 90 degree. Here we can see these beams are broken as we have used quick draw beam option, so we can join them using this one. Now we can select this portion, then replicate to the story first floor, apply, go to first floor, quick draw slab, this one, using this option we can draw slab for this portion. Using this option we can draw slab in this way, like this. Now to model stair we can go to plane beam. Starting of the stair will be from this side. From this grid the starting of stair is about 1.2 meter, like this. Then divide this beam into two portions. We can add reference plan for making landing level, add or modify. From here go to modify or show grid system, reference plan, add, ordinate will be 1.8 plus our ground floor height is 3.4 meter, so half of this 3.4 meter 1.7, so it will be 3.5. ID landing 1, click on OK, OK, OK. Go to reference plan, from here draw landing beam, then select this one, replicate downward minus 1.2 meter, apply, then break this frame into two parts. Now draw stair portion. We can define separate slab for stair, add copy, write ST 200. We can design stair first, accordingly we can provide the stair waist slab thickness here. I am considering 200 millimeter here, click on OK, OK. Now select this one, from here to here, here to here. This portion we can delete. We will start our stair flight, press enter. Here we can see the stair generated. For second flight we need to go to first floor and replicate the beam, divide into two portions. Now delete this frame, go to reference plan, press enter. Our stair modeling done. Now here we can apply our loads. go to checklist, mesh source. If we apply lateral loads, in that case we have to define mesh source. This building I will design for vertical loads only. I will not apply lateral loads. If you want to see how to apply lateral loads and accordingly if you want to design high-rise building, you can follow another tutorial I have. Go to my channel and go to playlist. Created playlist. You can watch this one, 10-story building design course. This one. Here you will see how to apply lateral loading for building design according to ACI code. For IS code, follow this one, building design course on IS code. This one. Here you will get full course to design this high-rise building including lateral loads and response spectrum analysis. Okay, now as I am not going for lateral loadings, I will skip this step. Now come to loading, dead load, floor finish 1.5 kilonewton per meter square. We will apply floor finish, so go to define load pattern, floor finish, super dead, this one superimposed to the structure, so floor finish will be super dead loading. Add new, wall load as super dead, click on OK. Now select the beams where we will apply the wall load according to the architectural plan. For example, these beams are having walls. So now click on this frame load assignment, distributed wall load. The wall width is 23 centimeter. As our floor height is 3.4 meter, if we deduct the beam depth, top beam depth 40 centimeter, then the height is coming 3 meter. So we can calculate here 0.23 into unit weight of brick wall 18.5 kilonewton per meter cube, then wall height 3 meter, so it is coming 12.765. this value we will apply 12.765 kilonewton per meter. So here our beam width will be 25 centimeter. In BS code practice, the beam width is 20 centimeter. Here we can edit this one, 25, 25, 25, 25. Click on OK. Click on OK. For stair, we can apply the loading for stair. For stair, floor finish 1.5 kilonewton per meter square. Live load, we can use previous selection option. Live load will be 3 kilonewton per square meter. 3 kilonewton per square meter. Now for this floor of residential building, we can apply live load floors 2 kilonewton per meter square. 2 kilonewton per meter square. For wall, we can select click joint in XY plan. In this way we can select our beams Then we can deselect the beam where there is no walls. Apply the load. Same this floor height 12.765. We can go to select this one, stories, first floor, select, then replicate 2-story second floor like this. In our plan, 2 floor height is 3.4 meter. This one and this one, ground floor and first floor. Next floor height is 3.2 meter. So the wall height will be 3.2 meter minus 40 cm of top beam depth. So in that case, we can type here 2.8 meter wall height. So 11.9 kilonewton per meter. So we can select our beams. Then wall load, replace existing loads 11.9 kilonewton per meter. We can select the story, then replicate 2-story third floor, go to third floor. Here this slab outline like this. We have cantilever portion also this side 1.2 meter. So that one we will add offset 1.2 meter, draw slab 175 like this, and here we can model none line to apply load if there is no cantilever beam, or we can define null beam with negligible weight and properties. Then we can apply wall load. For example, the height of wall here 2 meter, so 2 into or 1.5 meter, 6.4 kilonewton per meter. Same here, this portion 6.4. This one we can replicate to the story 2F and 3F. Here select frames and apply 6.4 kilonewton per meter for 1.5 meter height of wall for balcony. Now at third floor our slab area will be reduced, and this side 3 columns will be deleted. This portion we can directly move to this point by selecting the joint, then click on move, pick 2 point from here to here, apply like this. Now select the story 3F, then replicate to story 4F and stair top also, apply. Okay, here in the stair top we can see our plan. These 6 columns are available, so this portion we will delete. Here this slab will also be deleted, and this one will also be deleted. Now here the wall height will be 2.8 meter because the stair top story level height 2.8 meter. So this wall load will be changed 2. Here we can see the story height 2.6 meter. So 2.6 minus 40 centimeter beam depth, so 2.2 meter height, 9.36 kilonewton per meter. Select this one, this one, this one, and this one, then apply 9.36 kilonewton per meter. And this portion, the load will be changed. If the parapet wall height is 1.5 meter, then we can apply 6.4 kilonewton per meter at periphery of the roof. 0 apply. Now select the periphery of roof, then apply 6.4 kilonewton per meter. This was not selected, so now select and remove the wall load. So this one our roof, and this one stair top. Go to here, we can remove wall loading 0. If there is overhead water tank on top of the slab of stair top, then we have to apply water loading. That water loading calculation and application I have shown in the design course. I have shown here this building design course on IS Code. Here you can see the procedure of applying water loading on top of the building. Here I am not going for that one. Slab, stair top slab, and here we have some beams for architectural design. Here 1, 2, 3, 4 beam. So we can click on this continuous beam 20 by 50, number of beam 4, and parallel to X, like this. Our modeling is finished. We can check our loading, dead load and live load. Live load for this area 2. We can select all the stories because we have not applied load for this cantilever portion. Live load 2 kilonewton per meter square, floor finish 1.5. Select all the floors, apply floor finish 1.5 kilonewton per meter. So here we can see floor finish 1.5, live load 2, and for stair 3. To see wall loading, click on this wall load like this. Following the IS code, you can apply the lateral loading, and here I have kept all the data for applying lateral loading, CP calculation for wind load, and for seismic loading the value of Z importance factor, and site type, all the things you will get here. Mesh our floor and stair. Select object type floor and wall. Here stair flight modeled as wall section, so select floor and wall, then go to assign for shell floor auto mesh. If we go for default, we have to change the default meshing. We will go to analyze, here automatic mesh settings. We can use rectangular mesh or we can go for general meshing. This one quadratic or triangular meshing. Mesh size we can choose 0.3 meter. Click on OK. Then assign this one default, apply, and previous selection. In this time we will assign wall auto mesh, auto rectangular mesh. We can go for 0.3 meter. Okay, now save the model. Now we can check the model if there is any warning available or not. Analyze, check model, select all, click on OK. No warning message were generated. We can remove horizon from our view. Horizon, apply. We can change our 3D view using color option like this. We can extrude our view in this way. Frame design type. Now we will check the checklist. We have done meshing. Before going to analysis and design, we will provide stiffness modifiers to consider the structural members as cracked section. This has to be done as per design codes. For IS code and ACI code, almost the stiffness modifier factors are same. Provide stiffness modifier for column. Select the object type columns, then assign frame property modifiers. Here J torsional constant 0.7, 0.7. This modifier for design. For serviceability check, modifiers will be changed. To get clear idea about stiffness modifier, you can check some videos in my channel. Go to videos, here search stiffness modifier. Here you can see stiffness modifier or cracked section analysis explained in Etabs. And another one available, awareness on using stiffness modifiers in Etabs. These two you can check for further knowledge. Apply. Now for shear wall, there is no shear wall. For beam 0.35 and for serviceability check 0.5. Now we are going for design, so we will use this one 0.35. Select the beams, then assign property modifiers 0.35, 0.35, 0.35. Apply, and then for slab 0.25. Select object type floors, assign shell stiffness modifiers 0.25, 0.25, 0.25. Apply. Okay. Now save the model. Now we can go for analysis and design. Run the analysis. We can go for design. Here the preference already we have assigned IS code. Go for define load combination. We can add default design combination as per selected IS code. Concrete frame design, slab design. If shear wall available in the model, we can select concrete shear wall also. Click on OK. And for foundation, we can add manual combination dead load plus live load. Dead load 1, this one self weight, floor finish 1, wall 1 and live load 1. Click on OK. Then from here also and from here also we can start our design. Here all the columns and beams have been passed. We can check our rebar percentage. Select object type, columns, show selected object only. Here we can view our design result for columns. We can remove grid visibility from here also. Display rebar percentage, apply. Here we can see rebar percentage. By checking the rebar percentage, if we want to reduce our section, we can reduce. For example, here this column 0.8% minimum reinforcement, this column we can reduce its section size, and for this column 3.91%, this is more than 3.5%, so this column we have to increase to reduce its percentage below 3.5%. as this one low rise building, so it is better to keep our rebar percentage below 3.5%. For high rise building we can go up to 6% or in some cases more than 6%. This column select, unlock the model, assign column, modify, add copy of property C 25 by 30, here 300. Click on OK, and another column, add copy 600 C 25 by 60. Okay, now this column 25 by 30, this column also, and this column we will change it to 25 by 60. Now we can run the analysis. concrete frame design. Now we can check display rebar percentage. Now this is okay, this one also okay, and this 2.01 2.23%. So in this way we can optimize our column section size. According to this design we can do detailing. We can go for column detailing. Our section size is 25 by 30. We can make it little bit larger. Rebar number 6, number 14, and links or type this one number 1, and the tie bar and spacing, this one we will check. Go to column main bar. Here we have two column having same section 25 by 30. So we will make group for these two columns. So we have to consider the maximum reinforcement among these two column section. Here 0.8% all through the column. Here at top this 1.06%. You can ask why the reinforcement at top floor more than the lower floors. In that case you can read this article at decodebd.com. You can go to blog. Here I have posted several blogs on important topics. Here this one, why does required column reinforcement in upper story appear higher than the lower story, and what are the solutions? Here you can read the reason and the solution. Okay, if at top story the required reinforcement is higher than lower story, we have to provide the higher reinforcement amount all through the column from upper story to lower story. We will check rebar area. This one 793 millimeter square. Required area 793 millimeter square. Bar, here number of bar 6 and diameter of bar 14 millimeter. So the provided rebar is 923.63, which is more than this one. So this okay. 6 number 14 main rebar, and for tie bar we can go to column tie bar. Here this one as per ACI code and this one as per IS code. Column width 250 millimeter, depth of column 300 millimeter, selected tie rebar 8 millimeter, provided smallest long rebar dia in this column is 14 millimeter. Required shear reinforcement from Etabs. This one we will go to display design info, shear reinforcing, apply. $277 along shorter direction, and along longer direction 332 millimeter square per meter. So here maximum on 332, 332 or 333. This one required number of leg used 2 leg. According to the design code, minimum shear reinforcement to be provided. These are the checks, and at last we can decide the required spacing 200 millimeter center to center. So here we can type this one 20 center to center. This one C1. For larger one we can check this one, shear reinforcement 665 for 600 millimeter long column, 250 by 600 millimeter, tie bar 8 and smallest long rebar. So main bar we have to design first. Display long bar. We will consider the reinforcement above plain beam level because this portion we have modeled to design our plain beam or grade beam. Here required reinforcement is more because of short column effect. If we do not need to design grade beam, we can start our modeling from finished ground level. That means from here bottom story height 3.4 meter and typical story height above the ground floor we can provide accordingly. As we design plain beam or grade beam from Etabs, that's why we consider foundation depth as the bottom story. If we design with this one, that will be enough. Otherwise, if we consider this reinforcement, this will be over design. 3016 millimeter square. 3016 millimeter square. We can find out this 20 by 60 here. For example, this one C3. This one increase 25 centi. We can increase our rebar along this direction also. Here link or tie bar here 2. That means 4-legged. 1, 2, 3, 4. Here now it is coming 12 number of 14 millimeter dia bar. 12, 14. It is coming 1847.26. So we have to increase the diameter. Still not okay. If we provide 12 number of 18 millimeter dia bar, then it is okay. Now go for tie bar design. Here 18 milli dia bar and required shear reinforcement from Etabs 666. Here we have used 2 tie bar, so leg will be 2 into 2, 4 legs. So if I provide here 4 legs, here the required spacing is coming 250. So here also you can provide 200 millimeter center to center. This is okay. In this way we can do column design and details. Now we can go for beam design. Go to plain beam level, show all object. Here we can see the required reinforcement area for the beams. Here you can type the name for the beam. This one P1 for plain beam. Like this. Here we do not need to scale it to look smaller. in layout we can adjust our view like this. Okay, here we have 1 2 3 4 5 of span. 1 2 3, here it is 3 span. We can add more 2, copy like this, like this. Here in this span this is 25 by 60. So here we can type 25 to 60. Here this span is 60. So in this way we will draw our section size. Now we will design our rebar. All along this 25 by 50 section, 333 square meter rebar required. We can reduce this section size, then we can redesign to check. If it is okay, then we can proceed with the reduced section size. Now I am proceeding with the same size, 333 for these beams, and for this one 25 by 60 section 405 top and bottom. Now go to beam main bar. This one imperial unit, this one SI unit. Top 333 333. And last one here, using this 2 span we can continue up to 4th span, 5th span. The required rebar is 405, 405, 405, 405, 405 and 405. Now we can choose the top main rebar 2Y16, that is 402. More than this is okay. So no extra rebar is required. If we choose 14mm dia bar, then extra for 14mm dia bar is required at top. 14, extra one required here, 14, extra one, 14 here also required. In this way we can design main rebar for our beams. Here 402, so we will continue 14mm main rebar all through the beam. Then we will choose our extra rebar number 2I14 114 461.815 square millimeter. So this is more than 405. So this okay. This is 2I14 rebar area which is less than the required. That's why extra one 14mm dia is required. So here you can see all through 2 Y14 and one extra Y14 is required for the beam. So here we can write 2 Y14, then 1 14 extra. In that case we can add one bent bar here like this, because this will represent the extra rebar at top. Here 1 Y 14 14, here 2 Y 14 at bottom. In this way we can do our detailing for beams. We can run the design for slab first floor. Okay, here top rebar intensity millimeter square per meter. We can see the flexural design direction 2 top rebar. If we impose minimum reinforcing, we can click on this, then apply. It will show minimum required rebar at top edge. In bottom rebar, for bottom rebar, click on apply. These are the bottom rebars. Go to the Excel sheet. We have designed slab thickness. If there is heavy load in the slab or floor, in that case we have to check the deflection for this slab thickness. If there is no beam, if it is flat slab, in that case we can check punching shear. Now go to slab rebar design. Thickness of slab 17.5 centimeter. We have the standard detailing from edge to this cranked portion L by 7. For the interior portion L by 4, L by 4, and short direction bar, this one 4.7, this one 5 meter. So this direction is short direction bar marked with A, long direction bar marked with B. The extra top rebar can be marked as 1, 2. 1 for extra, 1 number of rebar, 2 for if there is 2 number of rebar required. In case of in cantilever, in top portion we need more rebar, so here as per design maybe 2 extra top rebar will be required. We will see from the design. Now just making the sample detailing like this. This one will be 2. Now let's do the design. Go to the Excel sheet. Here minimum required steel ratio 0.0018. You can check the specifications. Now AS mean required as per the slab thickness. So rebar required at top is 315, rebar at bottom middle portion 315 millimeter square per meter. From the analysis we can check direction 1 bottom rebar. We can check the slab direction. Here slab local axis, red 1, green 2 and blue 3. Okay, so this direction rebar is coming 262.5, that means 263, 263. Select rebar dia 10 mm, provide spacing, required spacing 249. We will provide 200 mm. So this one A will be, as it is alternate cranked bar, so this one will be like this. One is cranked and one is straight at bottom. So alternatively, one is straight at bottom, one is cranked. So alternatively, this spacing coming 40 centimeter at the top portion. So top portion required rebar at top edge, we will check. Go to display flexural design, top rebar direction 1. This one also 263. Required extra over the reinforcement provided 67 mm square per meter. So if we choose 10 mm dia bar, required extra rebar number 1. So one 10 mm dia bar we can provide in between cranked bar. So this one will be 1. Okay, and here we can write in similar way along in direction 2 also, that will be B, and if one number of bar required then it will be 1. In cantilever portion we can check, it will be direction 2, because this direction 2 top rebar, see here required rebar is more than minimum. We can take here 700 or 862 at direction B. Here at bottom we can first check bottom. This direction bottom is 265 or 63. Provided reinforcement 10 mm at 200 mm spacing. At top edge it is required 862. So required extra over the reinforcement provided 666 mm square per meter. If we provide 2, then it is coming okay. So here we can mark it as a 2, and here we will write 2. Here we can write 1 nose, 1 number, extra 10 mm dia in between cranked, here 2 nose, 10 mm dia bar in between cranked. In this way we can design cantilever portion also. If the cantilever is large, in that case we have to check the deflection. If the deflection exceeds, then here we have to provide more thickness for the slab. Here you will get the data for deflection limit as per the IS code and the ACI code. So in this way we can do our design of slab, and we can do the detailing using this Excel sheet and Etabs analysis result. So now slab also finished. One of the code BD viewer requested to design the cantilever beam. So for that beam I can show here. I forgot to show this cantilever beam design. This is the cantilever beam. The top rebar is more than the bottom rebar. So this rebar we can design. This is the cantilever, and here extend up to this portion. (615 millimeter square). Here 667. We can take this one. 667. 667. Our main rebar is 2y14. So at top the required rebar is coming extra 3y14. So we can provide here 4y14 in this portion. 2y14 plus 2y14 and another layer like this, 2y14. This one two side 2y14, this one 2y14. So in this way we can do cantilever beam design. And shear reinforcement we can check. (391). Here for beam shear reinforcement we did not check for normal beam also. Here in this case I am showing 277 all through. Here 405. Here 417. So for this beam can copy up to the end. Normally this A, B, A, this one we can type it as C. Here we can see from the design this 277 all through. So here we can write for IS Code is 250, beam width, beam depth 600 for this two portion, covering of beam 40 millimeter, rebar dia we have used 14, tie bar dia we can choose 8 milli or 10 milli. Here required 277. (417). Now if it is two-legged required 300 millimeter, we will not provide more than 200 millimeter center to center spacing. So this one will be 200, B also will be 200. Here A all will be 200. Here at the end this portion required is coming 241, we will provide 200. So all through it is coming 20 centimeter center to center 8 mm dia tie bar. B also same, and C also coming same for tie bar. Here this portion C, this tie bar. In this way we can design beam shear reinforcement also. Now we can go for foundation design. Now here go to the basement plan. Here combination for dead load plus live load, tabulated. Here force decimal place 1 taken. Okay, so this is our reaction value. Here we can go to single footing design first. If any single footing overlaps, then we will go for combined footing or raft footing. We will choose IS code. The unit will be in kilonewton and kilonewton meter square. We will go to table, reaction, dead load plus live load. This is node label. This one we can copy, paste, and here the reaction value we can Control C. Here this one mistake, this one press Control C and then paste like this. Now for reaction FZ, Control C, here Control V. Soil bearing capacity, for example 200 kilonewton per meter square. Okay, now required area is coming like this, square root of the required area, this. Now here we can choose our foundation size 1.72. this square size of footing we can choose 1.8 by 1.7. soil pressure coming 194, so 1.9 by 1.7. here 2.3 by 2, 2.4 by 2.1. in this way we will find out our required section size. Okay, according to this size we will model footing in basement level in Etabs. Now for foundation, file, this one save, file, save as. Now this support condition we can change, assign, restrain, we can now we can see the node level, joint level, this one 2, for this node 2, required size of footing 1.7 by 1.9. Here you can see the column orientation in this direction. First we can define foundation thickness, add new F 30 centimeter, 300 millimeter. Minimum footing thickness 300 millimeter. We will check punching shear. If fails, then we will increase the thickness of foundation. This one will be footing. Okay. Now for this node, rectangular floor, here we can provide the dimension. So 1900, 1700. Property F30. Now click on this. This support we will delete. Now for the node 3, required area 2.1 by 2.4. In this way we will check for all nodes and accordingly we will provide the foundation. I am providing average 200 2.2 meter by 2.4 meter. Select the corners of the footings. Select the properties, slab section. That's all. Then assign area spring, modify, add new properties for 200 bearing capacity. Now we will check the modulus of subgrade reaction. I will go for 2.5 for medium soil, bearing capacity 200. So modulus of subgrade reaction coming 20,000 according to the Bowell's assumption. So here 20,000, here already 20,000. So I will keep same as it is. Click on OK. OK. This apply. So area spring. Now previous selection. Assign shell. I will provide meshing. You can use this one, rectangular mesh, because all the size in rectangular shape. So 300 millimeter size. Okay. Now we can go for analysis. Now from here we can display soil pressure. Accurately we have provided 4 foundation size, this and this one. Now we will see for this 4 foundation. This one 182 maximum, 190, 176, this one 195. So our provided area is okay. Now we will go for foundation thickness. thickness check. Here this slab design, select stories for design base. Okay, now start design. Now we will check punching. This one okay, this one okay, below 1, and this one 1.15, so we have to increase this footing thickness, this one also. So which one is more than 1? For that one we need to increase the footing thickness. So unlock this one, we will assign shell footing thickness 45, and for this one define slab section, add copy F55, we will check with 55 centimeter footing thickness. Okay, assign slab 55. Okay, now we will run the analysis again. Now we can start design. Check punching, this one okay, and this one okay. Reinforcement design now. F1 length, width, thickness and rebar. Length 170 centimeter, 160 centimeter. Thickness we have provided 30 centi. Rebar A, or we can write here short rebar and long rebar. F1. Now we will do rebar design. Here single footing thickness F1 30 centi we have provided. Minimum required rebar 540 millimeter square per meter. Here we can check for this one. We can check bottom rebar 1872 outside of the column portion. We will go for strip design. Unlock this model, draw design strip, this one column strip, 1 meter strip for our design consideration. Draw snap option, midpoint, this direction, strip layer A, and this direction strip layer B. Here support generated, in that case we will remove the support. Now okay, now go for concrete slab design. We will go to slab flexural reinforcement layer A 1030 along this direction. So required A is from analysis result 1030. So for design, required rebar for design, this one, select rebar 12 mm dia bar, required spacing 209, so we can provide 200 mm center to center. So this one long rebar 982, long rebar 983, and short rebar 1030. Spacing is coming. This one will be 115, and here the selected rebar as per design, this one 109, 115. So we can provide spacing 100 millimeter center to center. If we increase the diameter 14, it will be 125, and this one will be 150. So we can write here short bar at 12.5 centimeter center to center, and long bar 15 centimeter center to center. Now we can go for combined footing design. This one, for example, these two footing we will make combined. 17 and 13, here you can see their reaction. 17 and 13, 338, 986. So here 17 and 13 node, (986) and 339. 86, 339. Soil bearing capacity 200 kN per square meter. Required area, this one we can check, 3.6 meter by 2 meter, 3.8 meter by 2 meter. Now it is okay. Soil pressure coming 192 kN per meter square. Center to center distance we can check, 2.8 meter, 2.8 meter. Here according to the load, combined footing is not required. If we reduce the soil bearing capacity, in that case combined footing can be required. For example, this one 4.4, 2.2, 4.8 and 2.2. This now okay. Here CG of load will be automatically calculated, and here X distance and Z distance from these two columns. So accordingly we can draw our foundation. So now here from larger load X distance is 1.68, and this side 1.32, 1.68. We can unlock this model, delete. We can draw a line